Hey everyone, my name is Jordan Adams and this is Sean Lynch.
And today we're going to do an experimental demonstration on commutated DC motors. For our experimental demonstration, we chose to design, build, and test a commutated DC motor, also known as a brush DC motor. Commutated DC motors have been around for a very long time, even dating back to the 1800s. This design is still popular today due to the fact that they can easily achieve various speeds by simply changing the applied voltage, as well as being relatively cheap and reliable. That being said, commutated DC motors also have flaws. These problems mainly occur when the brushes overheat from friction, requiring occasional maintenance.
These are our laws and equations that model the behavior of our DC motor. This first law, known as the Lorentz force law, describes the force exerted on a charged particle moving in a B field. The second law, or the magnetic force, stems from the Lorentz force law and specifically describes the force put on a current-carrying wire in a B field. And lastly, the torque equation simply models the torque, which is the force times the radius of the moment arm times the sine of the theta between those two vectors.
We first set the reference angle, shown in orange. Now, using the magnetic force equation stated in the previous slide, we can analyze the design of our commutated DC motor with this model. Knowing the B field as shown in green and the current directions in the coils of wire, we can see that the magnetic forces in blue will ultimately result in the tangential force shown in red, producing rotational motion and therefore starting the motor.
Now that our DC motor has rotated 45 degrees, we see some interesting things happening. Looking at our magnetic force cross products, we notice that this position gives us a larger tangential force, which are the red vectors, at each conductor. While there was significant force created in the previous position, this position is where we see the largest torque on our motor.
As theta shifts another 45 degrees, we can see that the forces are familiar, being that they are caused by the same uniform B field and having opposite directions of current on the conductors. Even though the top and bottom conductors have different current directions and forces, they will ultimately cancel each other out, giving the same resulting force as at the start of the motor.
Now that we are at 135 degrees, we are at one of the most critical points in the rotation of our motor. This is where our brushes, or the orange wire, switch sides of the commutator, or the copper ring that surrounds the rotor, thus reversing the direction of current flow. Notice that the cross products completely change and essentially reverse direction, but ultimately the torque is zero at this point in our rotation. While there is no torque here, motion still occurs because we have momentum stored up from the previous rotations.
Now that theta has reached 180 degrees, it is no longer necessary to show any more rotations. We can now see that at theta equals 180 degrees, we restart the cycle and equal the same resulting force as at theta equals 0 degrees.
By incrementing the voltage values from 7.5 to 20 volts, we calculated the speed to reflect the graph that's shown. Just looking at the graph, it's obvious that the data isn't absolutely perfect, but it is noted that the relationship between voltage and speed is linear. Also, the graph on the right shows the significant torque values of our motor as it rotates one complete cycle. Alright, so we saved the best for last, so enjoy the following videos of us demonstrating our DC motor. This is our DC motor running off of approximately 12 volts. Now this is our DC motor running off of approximately 20 volts.